Hi, in this video, we're going to begin talking about the binomial probability distribution, which is section 5.2 in our text. You can use your guided notes to follow along. The focus of this section is the binomial probability distribution and methods for finding probabilities. Easy methods for finding the mean and standard deviation of a binomial distribution are also presented. As in other sections, we're going to stress the importance of interpreting probability values to determine whether events are significantly low or significantly high. We'll also be going over some important calculator skills that will help you to find these calculations more efficiently. What is a binomial probability distribution? Well, a binomial probability distribution results from a procedure that meets these 4 criteria. The procedure has a fixed number of trials, where we're considering a trial as a single observation. And those trials, they have to be independent. So the outcome of one individual trial doesn't impact the probabilities of the other trials. Each trial has to have all outcomes classified into exactly 2 categories, and we call those categories success or failure. Now, thinking of success or failure, it doesn't necessarily always mean that one of those categories means you actually failed. The categories could be like left hand or right hand. Neither one of those is a failure. We just call success or failure as a label for our 2 categories. The probabilities of the success remains the same in all of these trials. The central problem of a binomial experiment is to find the probability of R successes out of N trials. So, like I said, we label success and failure. S and F are what we label them, and we denote the 2 possible categories of all outcomes. So here we have P of S is the probability P. And P of F is 1 minus P equals Q. So P and Q are complements because success and failure are complements. So therefore, their sum is 1. And remember, N in this case is the fixed number of trials. More notation. So X, sometimes we'll see it as R, is a specific number of successes in N trials. So X can be any whole number between 0 and N inclusive. P is the probability of successes in one of those N trials, and Q is the probability of failure in one of those N trials. So P of X, the probability of getting exactly X successes among N trials. And I'm going to ask you to get into the habit of not just writing P of X for these binomials, but you might have P of X equals some number A, like probability that X equals 5, because then we'll have questions also, not just equals to, but we might have probability of X is greater than some number A, or probability of X could be less than or equal to some number A. So those are all different types of probabilities we might find in this section. So the word success is used here, it's arbitrary, as I tried to explain before. It doesn't necessarily mean something good. Either the 2 possible categories could be called success as long as the probability is identified as P. So when you're using a probability distribution, because that term success can be arbitrary, you want to make sure you're always using X and P consistently in the sense that they both refer to the same category being called a success. Otherwise, it could get confusing and lead to mistakes. Let's look at an example. When an adult's randomly selected with replacement, there's a 0.85 probability that this person knows what Twitter is, based on the results from a Pew Research survey. Suppose that we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. Well, does this procedure result in a binomial distribution? And if the procedure does result in a binomial distribution, identify the values of N, X, P, and Q. So this procedure does satisfy the requirements of a binomial distribution. If you're asked to whether your procedure satisfies the requirements for a binomial distribution, you need to make sure that you're listing all of the reasons why. So we'll have on our next 2 pages here all of the reasons why. First reason is that there are a fixed number of trials, 5 trials. Next, these trials are independent because the probability of any adult knowing what Twitter is doesn't affect the results from other adults. The third criteria is that each of the 5 trials has 2 categories of outcomes. The person knows what Twitter is, we could call that success, or the person does not know what Twitter is, we could call that failure in this problem. For each of the randomly selected adults, there is a 0.85 probability that this person knows what Twitter is, and the probability remains the same for each of the 5 selected people. So, since we do have a probability distribution, let's label what our variables are. We have 5 randomly selected adults, so therefore our n equals 5. We want the probability to be exactly 3, so we would say x equals 3. The probability of success, or a person knowing what Twitter is, P of S, is 0.85. So whatever number denotes the probability of success, we call P. So lowercase p is 0.85. And think P for proportion. The probability of failure, someone not knowing what Twitter is, would be 1 minus P. Probability of failure, or Q, equals 0.15 in this case. Now let's look at an example about a game show. On a TV quiz show, each contestant has a try at the Wheel of Fortune. The Wheel of Fortune is a roulette wheel with 36 slots, one of which is gold. If the ball lands in the gold slot, the contestant wins $50,000. No other slot pays. What's the probability that the game show will have to pay the fortune to 3 contestants out of 100? Well, we'll eventually revisit this problem to find that answer. First, we want to know, how does the Wheel of Fortune problem meet the criteria of the binomial experiment? Well, there's 100 contestants, so there's a fixed number of trials, 100. N equals 100. The 100 trials are independent because the probability of any contestant winning isn't affected by the results of another contestant's spins. Next, each of the trials has 2 categories. The contestant could spin gold, that would be a success. We'll label that S. The contestant does not spin gold, that would be a failure. We'll label that F. And step 4, for each randomly selected contestant, there's a 1 in 36 probability that this person spins gold and wins a prize. And that probability remains the same for each of the 100 contestants. So therefore, the probability of success is 1 out of 36. The probability of failure is the complement to that, 35 out of 36. Note that the probability of success and the probability of failure are complements. We label the probability of success as lowercase p, the probability of failure as lowercase q. Remember, 1 minus p equals q. Our last criteria, the problem requires finding 3 successes in 100 trials. So that means it's meeting our central problem of the binomial experiment. Keep this criteria in mind. We're going to revisit the Twitter problem and the game show problem in our next video, using our calculators to actually find those binomial probabilities. So make sure you have this information and you have your guided notes worksheet, and we'll move on to video 2.